So in finite elements, we generally divide the volume omega into subvolumes, one of which is, let's say, omega e, and then the total volume is composed of the union of these subvolumes. E is, let's say, a generic element number. Now, I am going to introduce a slightly new notation. This notation is useful in situations where the number of degrees of freedom per node is equal to the dimension of the problem. That is, for a two-dimensional problem, the displacements u1 and u2 are the degrees of freedom at every node, and in a three-dimensional problem, u1, u2, u3 are the degrees of freedom at every node. In a one-dimensional problem, only u1 exists. So this is obviously the case with all problems in solid mechanics, in most problems in solid mechanics, and we denote the displacement in tensor notation. We denote it by ui, where I goes from 1 to 3. I will introduce another index which we will denote by capital letters, let's say capital I, which goes from 1 to the number of nodes in the system. So we will have quantities like ui capital I, which will mean the displacement in the ith direction at the capital ith node. Okay. Similarly, for other vectors and tensors as well, we will use a similar notation. Remember that these two things have to always appear together. So the direction and the node number has to appear together in every case, so that when we use shape functions at nodes capital I, the position of any point, the position vector of any point, denoted by its components xi, will be given by n capital I times x small I capital I. So this is the value of xi at node capital I, and that multiplied by capital Ni gives you the position ith position, ith coordinate of an arbitrary point in the body. Obviously, the summation convention with capital I is valid here and goes from 1 to the number of nodes in the element E. Okay, so the summation convention is valid. We could also have written, and maybe we write it like this in other finite element courses. We could have written it like this, with I going from 1 to nn. So x is equal to this, y is equal to this, and similarly z. So we had written it like this, but now we use a more compact notation using this capital I. We write it using the summation convention in this particular form. Right now, again, I want to emphasize that this notation is a bit cumbersome. It's not as elegant and as smooth as the notation that we have learned in the index notation that we use in Cartesian tensors. It's not as smooth as that, but it works in the case where the dimension of the problem determines the number of degrees of freedom at every node, and we are using the isoparametric formulation. In particular, when we use the isoparametric formulation, we use the same shape functions to map the position as well as the displacement. So if xi can be written in this form, ui can also be written in this form, where again ui capital I is the value of the ith displacement at node capital I. So with that understanding, these two equations make perfect sense. provided you realize that there's a summation involved here, just like in I, but the summation goes from 1 to the number of nodes, not from 1 to 3. Okay, with that, we can take this notation forward and write a few more things using it. So gradients of displacements, easy. Ui capital I are constants. So when you do ui comma j, the only thing that's a function of x is the are the shape functions. So you write I comma j u I. So this is how you write it. The small strain tensor epsilon ij is half ui comma j plus uj comma I. So you write it as half ui comma j is n I comma j, sorry, n I comma j u I plus uj comma I is n I comma I u j I. Note that this ji and this ii, the capital and the small has to always occur together. If you have a capital index, a small index has to accompany it, and they have to be looked at together. So this is your small strain, and similarly, this is your variation. This is your variation in u, right? So these are easily obtained. Now let us plug this into the virtual work equation. The internal virtual work, remember, was sigma ij delta epsilon ij dv over omega and omega e, let's say, for the element, and then del epsilon ij is half of n. So this is your del epsilon ij. But before using this, we can actually use the symmetry of the Cauchy stress tensor to write this as sigma ij, and we have done this before in we can write this as this, and then uh, because sigma ij is symmetric, we can see that this can be replaced by sigma ji, in which case this term and this term, j and I, both are repeated indices. So this term and this term are the same. So I can write this as sigma ij del, this is del u I comma j dv. So instead of the virtual strains, we can use the virtual displacement gradients of the virtual displacements. Now that's what we have done here, and once you do that, let me erase this. So you have sigma ij delta u I comma j dv, where you now write this as sigma ij n I comma j del u I dv. So I have used this with the del here to replace this. Okay, so that's what is written here, and then this is, sorry, this is not a function of x, y, z. So it can be brought out of the integral, and you are left with sigma ji del ni del xj. Okay, now use the same procedure for the external virtual work. Remember, the external virtual work is um, so the external virtual work is b dot delta u. So this is the external virtual work, which can be written as bi delta ui dv plus ti delta ui ds. So obviously, if your element does not share a boundary with the del omega t of the body, then this term will not appear. But let us do it in the general case. So this guy, you can now replace it by um, so this can be replaced, ui can be replaced by n capital I delta u I times bi dv. Similarly, this can be replaced as ti times n capital I delta u I capital ds. So this is how you can do it. Again, you can take this out. So delta ui I can be taken out. Delta u I can be taken out here. Okay, so that's what we have done here. Right. Now, the whole virtual work principle is internal virtual work equal to external virtual work. So this is your internal virtual work. This is your external virtual work discretized. And you can write the first one as a virtual displacement times a force. So this is a force which we call the internal force. So this we call Fii int, because capital I and small I are the free indices, j is the repeated index. So we will call it Fii int, and this part, so let's put a bracket here, plus, so this part is also a force which we will call Fii x. Again, uh, I and small I and capital I are the free indices here. So this is the virtual work done by the internal forces. The internal virtual work is the virtual work done by the internal forces, whereas the external virtual work is the virtual work done by the external forces, Fii. Now, del ni del xj, we can give it another name. So we can define bji, another tensor, as del n capital I del xj. Again, be careful. This goes from 1 to the number of nodes in the element. This goes from 1 to 3. Therefore, this is a 3 cross nn 3 cross nn matrix. If you want to replace it with a matrix form, this is 3 cross nn, not 3 cross 3. Please be careful about that. So we have defined this new tensor, and in terms of the new tensor, this is what your internal force becomes, and this is the work done by the internal force. Similarly, the external force uh, is this, as I have mentioned here. The external force is this, and your virtual work equation, since delta u ii is an arbitrary displacement, uh, your virtual work equation boils down to F external equal to F internal for the element. So F external and F internal obtained separately by assembling the elemental contributions, um, and you know how to assemble them from your finite element courses. The assembly procedures are exactly the same in nonlinear finite elements also, but this is a more basic equation, though it seems like obvious, but this is a more basic equation that will help us formulate the finite element equations in case of nonlinear problems. So remember, f external is integral over of bji sigma ji. So this is the sorry, this is the internal force, is this integral, and the external force is this integral, whereas this part would be zero if, of course, the element does not share a boundary with deltas omega t. Okay, so this is going to be our guiding principle. This is going to be our guiding principle in most of the formulations that we are going to handle.